Okay, hopefully everyone is nice and awake after having some lunch and some good sunshine coming through the windows. Tara must be pretty good at catching people when they're in transition, because I think you caught me also when I was in transition from over to Jacobs. So I've been with Jacobs for about 2 years, but I have about 13 years of experience in geothermal power plant engineering. It's been a really interesting day learning about all of the subsurface technology developments and what else we have to do in order to access that hot, superheated heat. And really, once we get it to the surface, you guys have done all the hard work. We can generate power from it. There are some complexities related to the geothermal fluid that will be coming up. So I'm gonna talk a little bit about those. So there's a lot of uses you could put this superheated steam to, industrial uses in hydrogen production and others. But I'm going to talk today about power plants, geothermal power plants. That's me. I'm the geothermal power market lead for Jacobs, and I have a chemical engineering background with a mechanical engineering license, but most of my role now is business development and marketing for Jacobs. And I lead a team of engineers, so shout out to them for helping me put this report together. So just real briefly, a goal of our report, and I think of all the reports, is to really support Clean Air Task Force in enabling policies and directing attention to where they should be putting their time and energy into the industry in order to push innovation and push towards commercialization of Superhot rock. So hopefully this report that we put together helps provide some direction on where we need to spend our time and energy in terms of things on the surface. So, like I mentioned, you guys have done all the hard work on the subsurface. So on the surface, we really know the technology on how to convert fluids with high enthalpy into power. So that technology is here. So what we focused more on was on optimization of the power plant itself, utilizing that superheated steam. So the first kind of phase of our study was looking at different types of power production and different. I'll talk a little bit about the different efficiencies between these methods of power production. We also took a look at cooling systems, what options we have available, and kind of the pros and cons of each of those. And then the real kind of meat of the report focused on our technology gap analysis, and I think there's definitely some room for improvement, but I see a lot of promise in moving forward with the technology. And then we did put together a high-level cost estimate as part of this study. So we took a look at 3 different types of technologies, and when we were kind of scoping out this study, we talked about a lot of different cycle configurations and kind of settled on these 3 to take a look at. So the first is the most simple way to convert a fluid that's hot into energy, and that's just directly put it into a turbine. So assuming that we're producing superheated steam at the wellhead, the first option we looked at was the dry steam plant, putting it directly into a turbine. So this is done in a couple of geothermal fields, traditional geothermal fields around the world. One is the geysers, where they actually are producing superheated steam. It's a completely dry steam resource. And they don't directly use that steam because of the impurities that's coming up with it. And so they actually wash the steam ahead of time. So they bring it, that superheated steam, back down to saturated steam, which is counterintuitive because you lose a lot of enthalpy that way. So that was the second option that we looked at in the geochemistry discussion kind of led us to want to take a look at that option number 2. And then the third option, in order to avoid some of the chemistry issues, putting steam directly into the turbine from the Superhot rock resource, we took a look at a binary cycle plant where you essentially put a heat exchanger in upstream of the turbine, and that means that you can use a clean closed loop cycle on the power system, and the only piece of equipment that would be seeing the potentially damaging geothermal fluid would be within the heat exchanger. So those were the three options we took a look at. The option number 2 is interesting. So at the geysers, they use about 2 to 3% of the steam flow is the wash water that they spray on the steam upstream of the turbine to bring it back down to saturation. So it's about 2 to 3% of the total flow for wash water. For the superheated steam at the temperature and pressure we're talking about for a super hot rock resource, we're talking about 15 to 20% of water, wash water required, which is a huge jump. And as we know, water is a sacred resource. And so that provides some kind of issues if we're taking a look at, if we're really concerned about water conservation. So just to go over some of the assumptions that we made, we put together some really high level models for the power plant, and we chose a very generic location, San Luis Obispo, California, more so to get some just real mild ambient temperatures for to model the project. We assumed 140 bar pressure at the wellhead at 400 degrees C, assumed 34 kilograms per second would be coming out of each well. We actually calculated the total amount of fluid that would be required for each modeling option, and then that determined how many wells we would need. And then the injection pressure we assumed was 155 bar. We did take a look at 3 different geofluids. First one was Fenton Hill. Second one is like very clean, pretty like groundwater or fresh water. And then the scenario 3 was modeled after the IDDP wells. So the geofluid chemistry doesn't affect the thermodynamics, but it does affect how we take a look at the materials that we're going to use within our power system. At Fenton Hill, there are high chlorides in that fluid. And then in the IDDP wells, it's got a very low pH, as you guys know, so it's very acidic and high. It has the highest NCG content or non-condensable gas content of the 3 fluids. So kind of related to some of the discussions that we've already had today, people have hinted at the geochemistry of the super hot rock resource, and that being an area that we really need to explore more and understand better what's going to be coming up with that super hot rock fluid. I think it's unlikely we will see as much volatility with what's coming up in the super hot rock resource versus traditional hydrothermal resources where they've been kind of, I imagine it, I'm an engineer, I imagine it soaking in the rocks underground and picking up a lot of chlorides and silica and that sort of thing. So hopefully we're not seeing as high of chlorides coming up, or non-condensable gases, so that we would have to deal with on the surface. Moving to kind of how we, very high level conceptual layout of the power plant and the well pads. And this was kind of based on what some of the literature coming out of the Forge site in Utah has been showing. And so each of these well pads shown around the kind of circle of the power plant have a supply well and an injection well, and there'd be 5 pairs of wells on each well pad. The nice thing about Superhot rock EGS resource is you can put your well pads closer to the power plant, whereas in traditional hydrothermal, your well pads might be located pretty far from the power plant, wherever your reservoir engineer decides that there's a good resource to tap into. So being able to locate the well pads close to the power plant eliminates some cost in piping and saves some pressure drop as well. So there's a lot of benefits to being able to locate the well pads close to the power plant. So the first model that we took a look at was the dry steam plant model. I do. Does this work?
It does. Yeah. Make sure it's on.
Okay. Okay. I'm just going to talk really loud. So.
Oh, no, there's a microphone there. Yeah. It's on.
Oh, that one's on. Okay. Sorry about that. So the superheated steam is coming in from collected from all those well pads. And so we show it coming into the power plant around 390, 395 degrees C. There's a little bit of pressure loss and therefore some temperature loss through the piping. We modeled 2 by 250 megawatt turbines in our process model. So you only see one here, but there is a second one. And so we're assuming that you would have to use 2 different machines to generate a total of 500 megawatts. And then once the steam goes through the turbine and exhausts through the condenser, we're assuming for these 3 process models that we were going to use some wet cooling with a surface condenser. Later on in the study, we do take a look at different cooling options, but in order to compare these 3 models, we just assumed wet cooling for all of them. And then eventually the condensed steam will end up going back into the Superhot rock reservoir system. So this is the easiest, most simplest solution for converting the Superhot rock resource to power. The other case that we wanted to look at is kind of the geysers-esque case. There's other fields that also do steam washing where they have a steam-dominated resource. And so essentially you put a separator here upstream of the turbine, and upstream of that separator you would inject water, and the water would bring your superheated steam back down to saturation. And what that does is it creates some droplets that will collect the chlorides and silica and the things that are coming up with the steam that you don't want going into your turbine. The problem with that, like I mentioned, is that you're decreasing your enthalpy in your fluid, which means you can't generate as much power from it, and it loses efficiency as well. So it's counterintuitive, but turbines like clean steam. They do not like geothermal steam very much. So a lot of operators have decided to try and clean that steam by steam washing it. So we ran that case as well. And then the third case that we ran was this, in quotes, a binary model. Um, Traditional binary power plants are usually used on low temperature resources. They The reason for that is you're generating fluid at a low temperature, and your secondary working fluid that actually moves through the working cycle is at a lower boiling point. So you generate steam at a lower temperature to move that through the turbine and generate power using that working fluid. And those working fluids can be hydrocarbons or refrigerants. In this case, it's a little different because we have a very hot resource. And the reason we wanted to run this scenario is if we can't send the steam directly to the turbine because of the chemistry of that steam, the turbine supplier can't design their turbine around those conditions, then one option we could pursue is putting a heat exchanger in. And then the secondary cycle fluid, instead of using like a hydrocarbon or refrigerant, we would actually just use water, but it would be treated water, clean, very clean water, like you would see in a conventional fossil plant with a steam kind of boiler. So the so the steam would be coming in actually to this heat exchanger here, and then we do show a separator. Depending on your temperature and pressure, you could have breakout of the non-condensable gases, so you may need to exhaust those, and that could lead to needing a gas removal system, which isn't shown here. But then you would just re-inject your fluid right back into the resource. So a fairly simple solution. So I'll talk a little bit about that. So summary of our results, we levelized everything against the direct use open cycle, directly using the steam. So you can see here that in each of the other cases, we use more geofluid in order to generate that same 500 megawatts. We also have higher parasitic loads from pumps and cooling tower fans. And then, so a metric that we like to use is this geofluid per megawatt. And so that's telling us that for every kilograms per second of geofluid, how many megawatts you can generate from that. And so you want that number to be very low. You want to use the least amount of geofluid that you can. And so you can see that the direct use cycle is the most efficient at converting the geofluid to a megawatt. The wash cycle is a little bit worse, and then the binary cycle is the least efficient. You can also tell we estimated, based on that 34 kilograms per second per well, we estimated the number of wells that would be required for each plant. So we all know that more wells means more money, and nobody wants to spend all that money. So I think that's all I wanted to mention about that. So moving on. Okay, so we did do a cooling system analysis as well. And so we looked at 3 different types of cooling options. The first being the natural draft cooling tower that you see a lot on conventional power plants, nuclear power plants, and for industrial use, but you don't really see them often on geothermal plants, and that's because they're pretty tall, and so they can be, if there's a community nearby, they might not want to see that big tower in the background. They also require a lot of pumping power to get the water to the top of that cooling tower so that it can naturally cool as the air flows up from the bottom of the cooling tower to the top. The benefit of a natural draft cooling tower is you don't need fans to pull that air up. So the parasitic load is nil for the fans, but you do kind of balance that out with a high parasitic load on the pumps that you need to pump the water to the top. The second option that we looked at is a forced draft cooling tower. So this is a very common design for power plants, geothermal power plants that have access to makeup water, and that's key. They need to have access to makeup water because you end up evaporating 70% of the steam that's coming into the power plant evaporates through the cooling tower, and so you need to provide makeup to inject back into your reservoir in a traditional hydrothermal resource. And then the third option that we looked at is dry cooling. So specifically air-cooled condensers. These are used a lot in geothermal and when the plant is located in a very arid condition or arid location. And so places like in the US and like Nevada, where there's not a lot of easy access to water, and water is very precious. So we use a lot of air cooling, and it also you don't get the evaporation losses that you do with the wet cooling towers. And so if water conservation is a big thing at the location of your plant, then air cooling is kind of the way to go. So the results of this study show that, which actually kind of surprised me, but the natural draft cooling tower and the forced draft cooling tower use very similar amounts of water. Obviously, the air-cooled condenser uses the least amount of water, a lot of that being the 5% makeup water that we assumed, which is lost in the formations. The parasitic loads for these various options, the natural draft cooling tower does have quite a bit of parasitic load, but it matches up fairly well to the forced draft cooling tower. The air-cooled condenser will have a lot of parasitic load because you'll need a lot of fans in order to condense, especially superheated steam that you'll be seeing. So the water requirements for a wet cooling system are about 20 times that of a plant using dry cooling. So you can see if water conservation is important to the project, that you really want to take a look at air-cooled condensers. Okay, kind of the meat of our report was doing a technology gap evaluation, and you can see here that there's a lot of 8s and 9s, which is exciting because power generation is not a new thing. We know how to do it, and we know how to do it well. The complexity comes in handling the geofluid. So I did want to point out a couple of items. The first being the gathering system piping. So traditional geothermal pressures and temperatures are very low compared to a traditional fossil fuel plant. So we're seeing pressures of 140 bar at 400 degrees C. That bumps up your piping class to class 1500. Comparatively, your hydrothermal resources would use piping class 150 to class 300. So the higher your piping class, the more money you're spending on your piping. So it's very important then to keep your well pads very close to your plant so you're not spending as much money on getting the fluid from the well pads to the power plant. The other item you'll see that needs some additional attention is the steam turbine, and so we put that at a TRL of like 5 to 6, meaning that the technology has been validated in a relevant environment, but it is not commercially used. So the 250 megawatt size turbine we kind of settled on because that's where the maximum limit. Steam turbines are being put into like more traditional power plants. In order to push, so in conventional geothermal, your limitations on the turbine are the fact that the steam coming in is saturated. So that can generate water droplets in liquid form. And when that hits the turbine blades, it's extremely damaging. On traditional power plants, they're using superheated steam, so you don't get any water droplets hitting your blades. So they don't need to design for that. The other item that you're designing for in a geothermal plant is the geochemistry. And so they have to use specialized materials inside the turbine that will withstand the minerals and things that are coming in with the geofluid. So one of the largest geothermal power plants for a hydrothermal resource is the Tauhara plant in New Zealand, and that is wrote it down here exactly what it was, 174 megawatts. But that's using actually 2 machines on a common generator. So there's lots of room for improvement for geothermal steam turbines to get them to the size that they will be, or that we want to see for super hot rock resources. I was just told I have 5 minutes. So I'm going to skip through that. So again, as you can see, technology readiness levels of all the technologies have either been proven in geothermal or they've been proven in conventional power cycles. So that's good news that there's not a lot of reinventing the wheel that we have to do. Really briefly, I'll just touch on the cost estimate that we put together. This was a very high level cost estimate. Really, since this is not new technology, once you get the turbine vendors to design an appropriate turbine for super hot rock, it's really just like operating any other plant. So we found out that operating costs are very similar to other geothermal power plants, and the cost per kW for the project hovering around $2,000 per kilowatt. That does not include the gathering system or the wells. So, but when you strip that away from the project, $2,000 a kilowatt is fairly reasonable for a geothermal power plant. So that's also good news. So a couple of kind of future scope items that we can pursue further in the future would be understanding, our water supply costs, and this can really vary depending on the location. But if we are losing some percentage of the fluid in the formation, then we need to figure out where can we get that water, how do we get it there, and how much does that cost. So that was something that wasn't included in our study. We also need future R&D around the turbine design. So the way to push turbine vendors to invest in more R&D is you guys on the subsurface have to prove that there is this amazing resource, and the vendors will come and follow. So it's a little bit of a give and take process to get to where we want to be. And then the 2 models that we put together are the quote binary cycle is an option that we can pursue further if it does not look like the turbine vendors can provide a turbine that can withstand a super hot rock geothermal resource. So then I think we should be pursuing both power plant configurations in case we can't design a turbine to directly take that steam. So that's what I had. Thank you.
When we chose this as a topic of 1 of 5, I think it may surprise some people because we all know that this is a relatively mature space. What could the gaps possibly be? For those that have the curiosity, I recommend you check out our LCOE report where we look out at nth of kind costs and why we think there's hope for $30 to $40 megawatt hour power production. And what you'll see there is the sensitivity analysis. As much as we love drilling technologies, and I do, even when I reduced it, I gave it a sensitivity, I took away 90% of the cost, and it changed my LCOE by 5%. That's it. What was the lion's share of my LCOE was the turbine. And that was me assuming a standardized off-the-shelf selection set, an nth of kind pattern. So not only do we need to get our turbine manufacturers to sort of, if we build it, they will come scenario of look at the size of this resource and how we're going to use it, but we need them to start standardizing, or else we might find ourselves in what the US is experiencing, the nuclear facility space, where we have bespoke models for everything and our prices are ridiculous. We need standardized turbine solutions. So that's why, one of the reasons we did this. Another thing I wanted to elevate here is why binary? Why consider this high temperature binary work? And this is almost a default out of my last trip here. I got to tour the facility. I don't know if you guys refer to this as a heat park, but the cascading use of the heat post-use of turbine. It's like I would write a love letter to Iceland about how amazing you continue to use and wring out every last drop of the enthalpy in this fluid. We're not seeing that on a global scale. And I think that heat exchangers may enable some uses. So I think electrolyzers for hydrogen, or DAC, or other uses that need ultimately a higher temperature working fluid, but it has to be clean. So this is the motivation behind why we wanted to really scope out that binary as well. So I hope this was helpful. I'll take just 2 questions in order to make sure we have time for Seth at the end. All right, Trenton.
So I noticed on the binary that the outlet of the heat exchanger was 300 C, and then you're injecting 290 C. So there's a lot of enthalpy going down the hole. And did you consider a second heat exchanger or an ORC or some other and that would really boost the productivity of the binary?
So when we were scoping out this study, we assumed that we would just model a very simple binary cycle that is not optimized for the solution or for the reservoir. So in reality, if we were able to fully optimize the binary cycle, you would see multiple, maybe high temperature and low temperature heat exchangers to really bring out every last drop of enthalpy from that fluid. So that's another kind of further down the road, something we can do to optimize that cycle and use more of that energy.
Sam, I saw your hand up.
I have a question about the starting point geofluid assumptions for 400 degrees Celsius, 140 bars. Seems like more IDDP1 type fluid characteristics. But if we would do the Superhot rock EGS, if the reservoir fluid is around 300 bars or 400 bars and 400 degrees, the enthalpy would be significantly lower, so around 2,000 kilojoules per kilogram. And once you would bring that fluid up to the surface, you'd be looking at probably more conventional type flash utilization. I was wondering if you considered that in your model, or like the only way you could keep it a single phase fluid would be if you kept the wellhead pressure greater than 220 bars. So yeah.
Right. No, we did not consider that. We assumed it would be superheated steam that would be generated, but that is another avenue we could explore, is keeping it under pressure and keeping it liquid.
That was a really hard scoping exercise. I agree. We toiled with that decision on pressure, and I appreciate the observations there.